Okay, so any questions from the lecture yesterday? Maybe you have a lot of questions. Okay, so today we'll start talking about the matrix computation. Coming back to the so this short course is focused on the sparse matrix, and the rest of the lectures is going to be a lot of sparse matrix. So the basic thing is what is a sparse matrix and how do we represent them? It's certainly different in computer representation. It's different from dense matrix. Dense is square, right? You have an array of two-dimensional array. But for sparse matrix, it's much more. There are a variety of flexibility in terms of how do you want to store them in memory. And then also there's a close relation between sparse matrix and the graph. So, and in fact, very often you use a graph representation. It's easier to do the operation. Okay, so that's this first lecture about a sparse matrix. So the question is where are sparse matrices coming from? And from our purposes, very often we see the matrices coming from PDE when we solve partial differential equations. But of course, this is not just coming from there, the sparse matrices. There are a variety of sources, and we'll not talk about too many of those. And then sparse matrix formats, the graphs we'll talk about, and we're talking about parallel distributed machine, right? So then the question is, how do you want to store a sparse matrix distributedly? Suppose you have a huge sparse matrix. How do you want to store it? So that's something we'll talk this lecture. Okay, so partial differential equations. I think a lot of you probably know this maybe even better than me. So essentially we can classify them into several different types of equations. The first type is hyperbolic problems. So this is usually like wave equations. So the sound wave, for example, you solve do the earthquake simulation and the seismic imaging, and very often you need to solve the Helmholtz equation. So that's the sound wave. And then for these kind of equations, people very often use the explicit time stepping method. So for this kind of method, you just look at your nearest neighbor of your discretization grid, and then do some averaging, and then you don't need to actually solve any system. So the solution at each point depends on the neighbors at previous time, for example. And then another class is elliptic. This is at the steady state problems. So for example, you compute electrostatic potential at a certain position. And here, everything will depend on everything else. And very often for this class of problems, we use the implicit method. And so this means locality sometimes is hard to compare to the first category here. So here you just look at the neighbors, and here sometimes you have to look at the global information. So the canonical example we're most familiar with is the Poisson equation. And here I have oh, sorry, my pointer broke. Does anyone have a pointer? My pointer broke. No pointer, okay. You have one? Okay, thank you. Thank you very much. Okay. Oh, sorry. Okay, very good. So here is a Laplacian operator, and I have a three-dimensional x, y, z. So it's a 3D problem. And then the last class is parabolic. This is very often it's a time-dependent problems. For example, you want to look at the temperature of this room at different location. It's depending on the position and also depending on time. So this parabolic is more complicated than this. It's very often underneath it involves elliptic solver, but on top of that, there's more. So then the thing is, the common method for those PDE, they are continuous problem, right? Unless for simple problem you have analytical solution, but very often you don't. Then you need to find a numerical solution. The first step to find a numerical solution is to discretize the domain. So for example, you try to solve the Poisson equation in this unit square, and then you put the mesh, a lot of grid points. So you want to see the, this solution on this particular location, and continuously, of course, your solution is a continuous function, but you discretize, so try just to find the solution at several points. And in this two-dimensional, you say, for each dimension, I put 20 points, like this. So then you use this finite difference in this particular case to approximate this differential operator. And then if we look at this one particular region, you have the center of this point is this guy, and then you have 4 neighbors, right? So for this center, this guy, in order for this position, basically x, y at this location, and then you see that I want to approximate this second derivative. So then you do this, look at the 4 neighbors. So that's how you get the difference, use the difference to approximate the derivative. And then we can look at this from matrix point of view. So we're looking at this ij position in the previous picture. And then this center, this point, is related to the 4 neighbors, right? One is on lower, one is on the left, one is on the right, one is the lower one is the upper one. So they're related by this. With this kind of, for example, 4-point stencil, then each point, each grid point will have a coefficient, when you use the 5-point stencil, the corresponding coefficient in this simple case, the center point is 4, and the other is -1. So then you get so you have a square of variables, and each one of those you can write out the equation like this. So you can have a square of those equations. And then the matrix, look at the matrix, is going to look like this. So at one row corresponding, one equation, one row corresponding to one of these points. And then you have the center guy is 4, and then the 2 neighbors and 2 lower neighbor and upper neighbor. So that's, you get the equation now. It's a discretized equation. Then you solve this AU equals to your definition of this F at each point. So then we look at some of the one I showed you is the simplest Laplacian equation, Poisson equation. They are very good algorithm to solve that. But then if you look at the very high-end application, then you can see the equations can be, the PDEs can be very complicated, and very often they are coupled. So I'll give you a couple of examples of some of the applications we're helping to do the simulation. So the first example is an international collaboration effort. So this is to simulate using the fusion technology to get energy. And this really, the research in this area has been going on for many, many years, maybe, I don't know how many years, 20 at least, I would say. So the motivation for this is really to get alternative energy, clean energy. Instead of relying on the fossil fuel, for example, then you generate a lot of waste, get a lot of carbon oxide, get global warming, all that bad thing. You get a temperature like this, you could get maybe 20 years later, get 45 degrees now. So that's the motivation for this work. And then it involves many countries, China, European Union, India, Japan, Korea, Russia, and the US. So the idea is to try to harness fusion, create a clean energy using the hydrogen as the fuel, okay, instead of using the fossil coal, for example, so using hydrogen. And then the promise of this is actually for this equipment, this tokamak, this structure they call, is when you input energy a certain amount, the promise is to get 10 times more. The output will be 10 times more. But currently, they haven't reached that point yet. So this equipment is actually, right now, is being constructed here in France. I think it's southern France. Do we have someone coming from France? No French student. Okay. So this is one place in southern France. Right now they're building this. And this guy, its predicted cost is about $10 billion. And then for simulation people, for scientists, scientists, they really want to do is to get a very good structure, very accurate simulation of this structure so that you can have a very efficient input-output. Otherwise, if your structure is not well designed, you may not get much output. Maybe your output could be even less than input. So it's not good. So that's one of the area we are looking at. And then one of the things we're closely working with the physicists, fusion physicists, is to predict the microscopic MHD instabilities when burning these plasmas in this equipment with a very high temperature. So in order to generate fusion energy, you have to burn this plasma in extremely high temperature. And then for particular, this physics is the efficiency of this fusion configuration, this tokamak, increases with the ratio of the thermal and magnetic pressures. Okay, so you want to have a higher ratio of this, but on the other hand, the instabilities is also more likely to happen when you have a higher ratio. So it's a very subtle physics problem. And then the thing is, these people, they have been building this simulation code. This code started more than 20 years ago. They keep improving. And that's a relatively newer code. They use a better discretization scheme. As I mentioned, the discretization, very often we deal with simple problems, but they have to do much more complicated. In this particular case, for example, the tokamak could be conceptually thought of as this toroidal, like a donut shape. So then what they do, the discretization, is they cut each of these plane segment as one plane at a time, and then connect together along the toroidal direction, the magnetic field connector from there. So then at each plane, they use, at each angle here, with a constant plane, they use a two-dimensional data. It's a two-dimensional thing, right? But then they use this very complicated 18 degree of freedom called quintic triangular finite elements. So it's not a finite difference. Finite element is different. It's a different kind of discretization mechanism. And then couple together all these planes along this circular direction. Okay, so that's the simulation. How do they do? And why is it a very difficult problem mathematically and also computing-wise? So usually when we talk about, in the beginning, I mentioned this Poisson equation. That's one equation, right? One type of PDE. But here, they need to solve all of these different kind of equations together. So this equation models a continuity, and that one is the Maxwell equations. And here you have to maintain the momentum, and given by this equation, all these physical quantity, like this is pressure, and that's the electric field, that's magnetic field, in that structure. And then you have to satisfy Ohm's law, and then the electron energy is modeled by this equation, and then ion energy are modeled by the other equation. So you see the objective for this complicated structure is to solve. You have to model all these physics phenomena and solve all these equations together. They call this coupled equation, coupled PDE. So it's not just the one type. And then you do the discretization for all of them at the same time. So that's why this nowadays they call this a multi-physics simulation. It's a very challenging problem compared with just doing one kind of elliptic problem. So that's one of the difficult problems, the finite discretization that gives a sparse matrix. So for that sparse matrix, the linear algebra problem we need to solve, the previous one, this ITER simulation, is they do the whole simulation is nonlinear equations. So then we discretize, linearize that, solve the linear system. And each linear system could be of size like 1 million or 2 million dimension. And then on average, each row, it's very sparse. It's maybe no more than 100 non-zeros. So you don't want to store your 2 million by 2 million matrix as a dense matrix. So the second example I'd like to show is also an international collaboration. It's building the particle accelerator. And what we are studying is to look at the structure of this cavity. They call this radio frequency cavity, and to design it in a good way so that you could, when you eject the particle, the electrons in very high speed, then they can have a very high brightness illumination when it goes through this structure. So this is one of the units in the International Linear Collider. Okay, and then depending on the So for this kind of the structure calculation, the underneath differential equation is Maxwell equations in electromagnetic field. Okay, so then the finite element for this particular simulation code, they use a finite element in frequency domain to discretize this structure, and then that leads to large sparse eigenvalue problem. Okay, so it's not just a linear equation. And depending on this structure, there could have a closed cavity, and it could have a cavity with openings. So for example, it's connected to waveguide, a boundary condition to several waveguide. If it's a closed cavity without an opening, it's relatively simple, so you get a linear eigenvalue problem. But then you, when they look at the frequency of the structure vibration, they want to look at somewhere close to a certain point, certain frequency. So that means your eigenvalue problem is actually trying to find the interior eigenvalue. It's not try to find the largest eigenvalue or the smallest eigenvalue. So, and finding, as you learn from, I think Ren Kan in his lectures, probably he mentioned the eigenvalue problem to find interior eigenvalue close to this sigma is actually more difficult numerically than finding just the extreme eigenvalues. So this is one type. And another type of cavity is with the opening here, then your nonlinear eigenvalue problem is actually complex. And depending on how many openings you have, then you could have different level, could be quadratic eigenvalue problem, or could be even higher degree. Like you with the 3 openings, you can have, highly, how do I say, it could be 3 polynomial of 3. So the equations, if you look at closely, is Maxwell's equations, and here is the electric field. We want to compute the field vector, and with find the frequency and this field vector. Frequency is given by this quantity. So find the frequency and the field factor of normal modes along the normal direction. Okay, so that's described by the Maxwell's equation. And for this particular simulation code, they use a finite element, and this element is Nedelik type. So which means if you think about 2D, it's actually each edge is one grid point instead of each vertex of the grid is one variable. So here is each edge, or in 3D, it's each face is one variable. It's discretized. Then this electric field is represented as a linear combination of these normal vectors. So then you write this out. It's this generalized linear eigenvalue problem. So you have a matrix pair, K and M. It's not a standard eigenvalue problem. So that's the closed one. For the ones with waveguide boundary conditions here, then you have another, so you still write these Maxwell equations here, but this P term has more involved. So in the previous one, this P term is just here, right? So now this P term is given by several terms, okay? So that your frequency here is not just the one k square, so has a polynomial in there. That's why it's a nonlinear eigenvalue problem. So you write down this, and in fact, there's a complex term corresponding to the complex term. So there are two terms with a complex. And then it's a nonlinear eigenvalue problem. It's pretty complicated. Look at this. So those are just to give you some motivation about some of the high-end simulation and what kind of PDEs they have. And it can be much more complicated than what we think about just the Poisson equation or Helmholtz equation. It can be more than that. So then we say look at the matrix. So all these after discretization is sparse matrices, right? And then it comes from many different applications, even not from PDE, like chemical process simulation. It has, from optimization, numerical optimization, you have a lot of these sparse matrices. And nowadays, when people do big data analysis, then they have sparse matrices also. So there's no clear definition of what do you mean by sparse. So, but in reality, in practice, very often we see a sparse matrix could be of dimension, the matrix dimension could be like a million, right? But then if you look at each every row, you get only like no more than 100 non-zeros. So you really want just to store those non-zeros to operation only on those non-zeros. So for example, these are two matrices from different applications. One is from Boeing company when they do the airplane design using this MSC software. So this coming from structural engineering. Then the sparsity pattern. So what I plot here is each of these guys corresponding to a non-zero. And the different color probably corresponds to the different numerical value, the quantity, the absolute value maybe. And all these blank stuff, they are zero, okay? So for this structural engineering, you got a relatively regular pattern. It looks like nicer to deal with. But for chemical engineering application, this one, then you get the pattern is very irregular. It looks like more difficult to deal with than this one, right? Okay, so now we look at for sparse matrix computation. Essentially, we have to design the algorithm, the storage, representation, everything, in order to deal with any pattern. So we don't want to restrict ourselves to say you can only work on. So you don't want to say that you can only work on this pattern. Instead, your code cannot work on that. So that's not very nice. So that's what the goal here is, to get a general representation to deal with the general matrices. So we assume the sparsity pattern is arbitrary. And then here I give you some notation. One is n. I use n to denote the dimension of the matrix. And NNZ is the number of non-zeros of this matrix. So there are some obvious choice. So you can say that I can use people usually straightforward way of thinking is to use a triplets format. So I will represent in this format. I will represent each non-zero. I know the row index, column index, and give the value. So this is a triplet, right? And then to represent this as a 3 arrays. But so the storage requirement for this, you will need 2 times the number of non-zero integers corresponding to, so there are only a number of non-zeros is the total number of non-zeros, and then 2 times this to store this ij indices, right? And then you need a number of non-zeros of reals, depending on whether it's a single precision or double precision. So this is a nice straightforward for people to use, but then from algorithm point of view, it's actually not very easy to randomly access one row or column. You can think about it. So another storage scheme people think about is linked list. So you can say I have a non-zero, and then I have a link. I have one entry of this non-zero for each guy, and then I have a list to point to the next non-zero, and then a pointer to the next non-zero, and then link them together. And linked list, this kind of concept is used a lot in computer science. And in the beginning, people just use this, say, we'll use this for sparse matrix representation. But in fact, you can think that with this representation, when you do matrix operation, you cannot very easily to call BLAS operation. Remember the BLAS dot product, SXP, and GEMM, and those require your matrix entries to be stored continuously. And you cannot say I have a pointer to somewhere, then call this a BLAS. So that's not good. So those are not actually used in all the code. So in code, we use several different formats. One is called a compressed row format, for example. So I give you a small matrix here. It's a 7 by 7 matrix, and only those guys are non-zero. The other is 0. So compressed row format is I go through this row by row, and then I store only the non-zeros of each row. Okay, so here, the non-zero value array, it's a linearized one-dimensional array. I store 1A and 2B and CD3, so like this. So that's I store only the non-zeros row by row. And then for each non-zero, I have a column index value. So in this case, the first one, non-zero, the column index 1 is 1. Then this non-zero column index is 4. Okay, so you get the second row, the column index is 2, and then this one is 5. So the last row here, KL7, right? The corresponding index is 3, 5, 7. Okay, so there's non-zero values and the column index, but only these two guys, the two arrays, they are not enough for you to figure out, for example, what's the row index of this. So there's another array of row pointer, and this array size is smaller than number of non-zero. You only need this to be n, and I use one more as an end marker. So this one is really pointing back to these two arrays. Say where is the beginning of each row. So for example, the first row is beginning in this array starting from 1. The second row will begin in this array starting from 3. Then the third row will begin starting from 5, right? Is any question for this? Okay, so that's pretty clear. So this one is just a pointer. If you have n rows, then you have n of these. The last one is just a pointer to 1 plus this. And then it's very easy to access, say, for example, if you want to access the fourth row, what do? So you go to, if you want to access the fourth row, which is corresponding to E45, right? So then you will come to this array, your row pointer array. Here I have 1, 2, 3, 4. So that means I start from 8, it will go to 11. So I start from 8, go to 11. These 3 elements will be the fourth row. Okay?
One row are all 0.
Which one? If all row is 0, is that right? Is the question? So the question is, for example, if the entire row is 0, that just means one of these two will be identical, right? So these two adjacent will be identical. And essentially, if you look at the 4th, 5th, the difference between the two tells you the row size, how many non-zeros in the row. If one row is entirely 0, then these 2 pointers must be the same. And similarly, symmetrically, you can, okay, so I want to talk about how do you do the operation with this storage representation. So I have the same matrix, these 3 arrays, non-zero value column index. And then, so you're stored by row, right? So I want to say, how do you do y equals to 8 times x? And x is a dense vector. So you have, so that's your a, right? I want to multiply this a by a dense vector x. How do you do that? Then the pseudocode could be this. So I have, because you store the matrix row by row, so you go row by row, okay? So you say from row 1 to n, this is the ith row, and I use a dot product version. For each row, I will accumulate the local sum, right? The sum will be starting from row pointer, the ith row, to the row pointer of the next row, I plus 1 minus 1. So this difference gives you the row size of the ith row. And then you basically need to multiply all of the non-zero in this row by the corresponding x component. But the tricky part here is that you need to match this non-zero. Since this non-zero in matrix is jumping, they are not like a dense matrix, 1 plus 1, 2, 3, 4. They are jumping in matrix indices. So you need to use this J index to find out which x value you want. So for example, if the J index says I'm the 5th, then you need to go to use this column index of that guy, of the column index, for example, one of the column index here, to find out I need to multiply with x. So then you see that here, x, you actually use one level of indirection to get the element. So that's a little more costly compared with the straightforward x of 3. That's only one memory access. But x of column index j is 2 memory access. You first need to fetch this column index j, and next to get x. Okay. So that's a little more involved than dense calculation. And then there are several points here. There's no locality for x because your column index is jumping from first row is 1, 4, second row is 2, 5. So your column index here for x is actually, you get x1, x4, x2, and 5, and x1 again. So you see that you first get x1 here, then later you get x1 again. They're kind of jumping back and forth once you go through this, the whole matrix. So there's not much locality for x, and there's the optimization can be done. But for the simplest form, you cannot do much. And the vector length is usually short. It depends, for example, depending on how many non-zeros you have in each row. And it can vary depending on different rows. So the vector length is short. And then you look at the kernel, the core computation here is, we talk about whether it's memory bound or computation bound. And here it's very clear it's a memory bound. So for example, look at this statement. I need 2 memory access here and then 1 memory access here. This is, you can think about sum is in the register. So you have 3 reads of the memory, and then you do only 2 flops. One is multiplication, one is addition, right? So it's clearly it's the ratio. If you look at arithmetic intensity, it's 1 to 1. So it's not very nice. And symmetrically, you can think about to do the column representation. So it's instead of doing row by row, you do this column by column store. And then you store all of them in this direction, column-wise, column-wise, you store them like in this direction. And then for each of these non-zero, you have a row index corresponding to this 1, 0, corresponding to this. And there's a column pointer pointing to the beginning of each column of this array. And it's an entirely symmetric representation. So if your matrix is symmetric, what happens of these 2 format? So it's the same, right? Suppose you are given a symmetric sparse matrix, you can use either. They are interchangeable. And then we can take a look at the sparse matrix vector multiplication. And here then you have since your matrix is stored column-wise, then you cannot easily really jump from row direction. So you really want to go column-wise sequentially access those elements. So that's why I write this loop. I will go through one column at a time, the outer loop. And then you can imagine that this matrix vector multiplication becomes, the kernel becomes a Saxby operation. It's one vector. So you one column, then this one column multiply the first element of x, and then add into the y. Okay. Then the internal internal calculation here is that for each column, I look at all the row indices, right? And then I need to multiply this each value of this all of these guys, multiply with this particular x of this the jth x, right? And then I need to add into this, depending on the row index of this non-zero, I need to add into the y vector. But now the situation is different from the compressed row. now your y vector has to be addressed indirectly with 2 memory access. And the x vector is actually sequential. Every time you just multiply 1 of x into this column. Okay. And similarly, what happens here? You look at it's still memory bound. And here you have 3 reads. I still have 3 reads. One is read the value, read this index of y, and then read the, I think it's y. And then I have 1 write, and then 2 floating point operations here. In fact, I think here is 2 reads, because this read you can read outside this loop. So it's 2 reads. Oh, sorry, so 3 reads. So 1 read is this one, and then 1 read is y component, and 1 read is this. So this is correct. It's 3 reads, 1 write, and 2 flops. Compare with, just 1 second. Compare with this. We have 3 reads, but there's no write here. With our write is accumulated in this register. And in the end, we put it back into this y array. So it looks like this one is slightly more efficient. Okay, question?
Yeah, just exactly the same thing. So the previous one is more efficient.
Right, that's right. Yeah, here I have 1 more write. Yeah, that's right. So then there are other representations. A good book to look at is templates for the solution of linear systems. How many of you are aware of this book? Yeah, that's very good. So I guess you are still not doing too much about computation yet, right? You're just beginning the PhD study, so right now just taking a lot of courses or something. So when you get to later stage, you will solve the linear system, for example, either using iterative method or direct method. So this book is a very good book that give you kind of guidance, what kind of iterative method you should use for different, depending on the different matrices, different problems. And in the beginning, 1 chapter of this book, it has the entire chapter is about sparse matrix representation. For example, what I didn't talk about is ELL pack and the segmented sum. And those formats are very good for vector machine. Remember yesterday we talked about SIMD machine and GPU machine. So those formats are very good for that. Yes?
So if you're coding in C++, is there like I go down with a sparse matrix class online?
If you're taking C++ class, you mean? Sorry, what's the question?
If you're doing your research in C++ and you don't want to reinvent the wheel, and with say like doing the matrix vector multiplication, do they have sparse matrix classes I can download online?
No, I don't. No. I'm not aware of. Yeah, for C++. But essentially regardless of whether any language you use, C or C++ or Fortran, so this representation is general. So for either C or C++ or Fortran, you treat this as a 1-dimensional array. For sparse matrix, you never think about it as a 2-dimensional thing, 2-dimensional array. Since for 2-dimensional, you have those zeros, it becomes holes in there. Then you cannot deal with this. So it's always a linearized, become 1-dimensional representation. Okay, so then apart from those, the storage scheme I told you is each element I store. And there's suppose your matrix to start with, you have some block entry with when you do the discretization, each discretization point, you could have several physical quantity. Like for example, 1 grid point, you can have the velocity, have a temperature, have pressure, and all these together. And in fact, for that grid point, you will naturally have a 3x3 dense matrix. So you can have multiple levels of this representation. So at the outer level, it's like a compressed row storage. But the inner, finer level, each of these entries is actually a 3x3 dense matrix. So that's what they call this block entry format. Each entry is a block. And there's a variation of whether you can have a constant block size or sometimes you can have a variable block size. Okay, so it's very flexible. And then another thing which is right now in the newer software code, it's not very used. But if you deal with a lot of this legacy code, in engineering code, in the early days, they used this skyline or profile storage. So meaning that they just look at this is sparse matrix, right? And you naturally, for example, if you deal with the Laplacian equation discretization, you have this 5 band. So they will say that we don't care about what's the internal structure within each band. We just look at the first non-zero of each row. So we store each non-zero, first non-zero of each row. And similarly, look at each column. We store the first non-zero of each column. And then within this band, within this, they call that a profile, we'll store everything. So even if sometimes you have a lot of zeros here, they still store that. So this storage is simplified compared with the general compressed row or compressed column. But then the thing is you waste some of the storage and operation because a lot of zeros here you included. What you excluded is really just those outside zeros. So it's less efficient, but it's relatively simple for people to work with. So I just want to mention very briefly, essentially just cite some of the results of the research done in this area. You think matrix vector multiplication, sparse matrix vector multiplication is a very simple operation. But in fact, people spend a lot of time try to optimize the code to speed up. Remember in the very plain CRC and CRS CCS representation, we said that internal operation, we have 3 reads, 1 write, and 2 floating point operations. So that means that you are very much a memory the memory bound, memory bandwidth limited. And what the people, for example, this group, Berkeley Benchmark Optimization Group, you can go to this website. What they have been trying to do is trying to use various representation, various blocking technique in order to overcome this, try to get a higher arithmetic intensity. So that means for each memory access, try to do more operations. So then the different optimization techniques that they have used, so one is matrix reordering. You can reorder the matrix so that you have a more closer, instead of saying spread out the non-zeros so they can be closer together. And then when you fetch the one item from the memory, your cache line could fetch several of the neighbors, and that gives you the spatial locality. So with this kind of optimization, they could get like a 4 times speed up over the traditional CSR representation. And then they use the register blocking, because in most of the computers, the register file can be large, could have like a 128 elements in the register. Then you can think about this register as a small cache. If you can utilize that, so people talk about cache blocking. Basically, they go down one more level to do register blocking. So find some dense blocks to do this, pad some zeros to do operation, and this could get a factor of 2 speed up. And then cache blocking could get almost 3 times the speed up. Then suppose you have multiple vectors, then for each memory access, you can do several operations. That gives you quite a few speed up. And let's say, suppose your matrix is symmetric, and then you store only half of the matrix, and then use this symmetry property to do matrix vector multiplication, you could also get a very good speed up. So these are just by reordering the code, doing a clever, reorder the instructions, etc. Identify some dense blocks. That will get the code. You can be like up to 6 or 7 times faster. So if you write a simple code, you think it's simple, right? But you don't get very fast. So we'll probably do a few minutes and then we take a break. So then we look at the dense matrix, and as I mentioned, the sparse matrix. The matrix actually has a very close relation with the graph. So here we look at define the graph corresponding to each matrix. So a graph is just consists of a set of vertices and edges, right? And this V is called the vertex set, and the E is the binary relation between on this V is the edge set. So then you can talk about 3 standard graph models. One is undirected graph, and one is directed graph, meaning that the edge between vertex I and vertex J has a direction, either directed from U to V or from V to U. And there's something called a bipartite graph. So this graph consists of 2 disjoint vertex sets, U and V. And then the edge is usually always directed either from one side of the vertex to the other side. So this edge is always U belongs to one set, V belongs to another set. It can be directed or undirected. So then your matrix we're talking about, usually we talk about square matrix, but it can be rectangular, right? So for rectangular matrix, the graph representation, we usually can use a bipartite graph. So you have a row vertices is one set, and a column vertices is another set. So then you can have like from row vertex to column vertex. For each non-zero, for example, 1, 3 is a non-zero. Then I put an edge from row vertex 1 to column vertex 3. So for rectangular graph, it's very natural to use bipartite graph because you have different number of rows, number of columns. You cannot really use undirected or directed graph. So bipartite graph is the most general, but then if you have a square matrix, then you can use either directed graph or undirected graph. So in this picture, I'm using the directed graph. For square matrix, I have the same number of rows, same number of columns. So I just have 3 vertices, each one corresponding row or column. And then for each non-zero, 2, 1, I will put an edge from 2 to 1, right? And there's also symmetrically 1, 2, I put another edge. So this is a directed graph. And then undirected graph. So for undirected graph, it can only model the matrix which has a symmetric pattern, okay? So if your matrix is a non-symmetric pattern, then you cannot use the undirected graph. So this is a little bit more restrictive. So you have an undirected graph here, and you have a symmetric pattern graph. So then you do 2 edges. If you have 3, 2, then you always have 2, 3. Then you can say collapse this 2 directed edges, consider as 1 undirected. So those are the graph representation. And then the thing is we talked about the matrix vector multiplication. And now the question is, how do you do distributed memory matrix vector multiplication, sparse matrix vector multiplication? So the first thing is we distribute the matrix. Suppose here I have 4 processors, and then my sparse matrix is this. And usually I divide the sparse matrix by block rows, okay, along this direction. So I give each block row to 1 processor. And then my goal here, the operation is I want to multiply this matrix A by this vector X. And my X is also distributed across 4 different processors. Okay, so they are not, so for example, this processor 1, I only see this part of the matrix and this part of X and this part of Y. And how do you multiply this part of matrix? I have to multiply this part of the matrix together with all the X vector and put in here, right? So that means some part of the X vector is actually not local to my processor. So look at the picture here. All the part of the X is local to my processor, but these, the second segment, third, and fourth segment, they are not local to myself, right? So the question here, when you design a sparse matrix vector multiplication, is the question you usually ask, which processors store all these entries, right? And then also which processors compute those. So each processor, someone has to compute the ith row here equals to row I of A times this X. This is a sparse dot product if you're thinking about sparse compressed representation. So what we do here is we partition the index set, this 1 to n, essentially partition into the different P subsets, right? So here I'm partitioning this into 4 subsets. And then for all of I in this each of subset, the processor K, I store those entries of y and I, x and row I of A, right? And then for all of I in this set, this processor K needs to compute this operation. And all of the row of A is local. I have everything here, but some of the entries of X is non-local. And then we have to do communication, send and receive. So that's the basic idea. So it will take some time. So let's take a break right now. There are several questions during the break. I think it's interesting enough. I'll mention to all of you. So the first question is about the dot product. Yesterday we're doing this OpenMP. It seems quite a struggle to get this. It's because I didn't spend any time to talk about this. We should spend some time, maybe this afternoon, to go through a little bit MPI tutorial and OpenMP tutorial. The programming model, how it's generated different threads is not very clear. So let me just say this. So remember in the program, in the beginning, I say OMP parallel, right? This just to say we will generate a parallel region. So the following region is a parallel region. We have maybe 3 threads generated. But then this pragma, this OMP4, this pragma is telling all these threads that this for loop will be divided among them. So if you have 100 loop indices, this 100 loops, then it's going to be divided among 3 of them. Each one will get 33 and one get 34. So that's the syntax of this. And that's different from you just generate a parallel region. And after you generate a parallel region, without doing this, you still don't know how many of these loops will be divided among themselves. So that's one thing here. And then if you look at the tutorial, in fact, you find out because this parallel loop, for loop is such a common thing. So they don't want to, you don't need, every time you see a for loop, you want to parallelize. You always do 2 things. So what they do is there's a new syntax called pragma OMP parallel for. So it's merged together. So these 2 things are collapsed. It does the same thing. It divides 100 loops among 3 threads. Okay, so you can just use, you can modify your program just with this one pragma, which does achieve these 2 things. And another question is about this graph. So that's interesting and simple. So why is the question here, oh sorry, I forgot to put this. So the question here is the first diagonal entry is 0. How do you distinguish in the graph compared to 2 and 3, right? So what you can do here to model this graph more precisely, you can say for each diagonal entry, if it's non-zero, I put a self loop, okay? So for vertex 2, you have a loop to itself, 3 has a loop to itself, but 1 doesn't have a loop to itself. But very often from later when we look at sparse factorization, then you will see that the diagonal entry, whether, from when we detect the non-zero pattern, etc., it doesn't matter too much. So we just ignore this. But for some applications, you probably want to be more precise with the self loop. And a third question is also very interesting. Is I was talking about this X vector is distributed among 4 processors, right? So then you need to communicate some components of X vector to processor 1, for example, in order to do calculation. And the question is, can we trade a communication or trade communication with memory? So I store the entire X vector on all the processors, meaning that I replicate this vector so that you don't have any communication at all. You can do that if you have enough memory, up to the point if you have, if you don't run out of memory. Because remember, the matrices we're dealing with, the dimension could be 50 million. So that means each of these X vector could be 50 million. And that's only one vector. And sometimes you probably heard about like Lanczos-Arnoldi. Then they have to deal with, when they build the bases, they have many, many vectors. The base, depending on the basis you build, could be like 100. So you could have 50 million by 100 dimension for these X vectors. And that's huge. So you cannot really store on one node. So it depends on your application. You could have, write your code in many different ways. You could duplicate the whole X vector or duplicate part of it, depending on how much memory you have. Or if you don't have much memory, you have to distribute it entirely like this. So it's all, in the spectrum of the code arrangement. Okay, so let's see. Because we talked about the graph, and then why a graph is useful. It's useful when we come to the next lecture. And it's even more useful. But here, even for sparse matrix vector multiplication, it can be useful. So the question here is we are talking about this entirely distributed X vector, right? And then you need some of the components of X needs to be communicated to one processor. So then the question is something technique we call the graph partitioning. So if you can partition the graph, basically reorder, relabel those vertices so that you minimize the number of X vectors which are non-local to me, minimize the amount of vectors which is remote, then you can reduce the communication. So then basically intuitively, I mean this is just a very high level intuitive statement, but technically it's very detailed. There are a lot of technical definition and then minimization, and it's very a lot of combinatorial algorithms. But just at a high level intuitively, what's a good partition of the graph? For matrix vector multiplication, a good partition, you want an equal number of nodes in each part. So here I want 2 nodes in each part. I partition to 3 processors, 2 nodes on each part. You don't want one node has one processor has 3 and one has 1 and the other has 2. That will be load imbalanced. And also you want a minimum number of edges crossing between the 2 nodes. So you can still think about this graph, think about a matrix vector multiplication. So the number of edges crossing these 2 nodes, 2 processors, is actually the number of X you need to get from the other processor, okay? So minimize this number of edges is good to reduce communication. And when you do this graph partitioning, minimizing this, what's the effect is really just relabeling your vertices, and then you similar like you do a symmetrical permutation of these matrices of row and column. So instead of 1, 2, 3, 4, 5, 6 as this, maybe you store it as 1, 3, 5, 6, 2, 4, and similar 1, 3, 5, 6, 2, 4. So it's a shuffling. Okay, it doesn't change the matrix property. So it's like reorder the rows and columns by putting all the nodes in one partition together. And then after that, so the best matrix reordering, you will get, this is the best scenario, block diagonal matrix. Then you don't have any communication, so every X is your local, right? But of course, it's in the reality is you cannot get this the best situation. So the best ordering may be you have some of the non-zeros here at the neighbor. And so for example, if you can have a reordering which minimize the bandwidth, then you only need to get X which is at your neighbor here, but you don't need to get X which is far away. And that's a little bit communication, but slightly better. So essentially we say ideal matrix structure for parallel is block diagonal, then you don't have any communication. And so a better reordering probably you could get is most non-zero in a diagonal block, but a few of them outside.
Quick one.
Yeah.
To actually go through this reordering, is that very expensive?
It's very expensive. I wouldn't say it's very expensive, but it's a lot of algorithms. So in fact, for this course, I would talk a little bit graph partitioning, but it's not too much, and there are good graph partitioning package to do this. I don't know whether you have heard about Metis and the Scotch. I will mention those later. Have you heard about this? Yeah, that's good. So some people have used this. Yeah. So they can do a nice graph partitioning, and then give you a much better compare with you start with a random the matrix with a random pattern, and they can probably do some ordering, try to clutter everything close to the diagonal, so we have a much better property. And this kind of format is not only good for communication, but even on one processor, sequential code, it's also good because you have locality access to X. Remember when we look at a CRS or CCS, you are jumping your CRS actually, you are jumping your X vector. So you jump X first component's fifth component, and after a certain time, you come back to 1, 5 again. But with this, you don't jump. So suppose you have all the non-zeros diagonal and just the off-diagonal nearest neighbor here has non-zero. So you access X is just here, and then from here to here, and here to here, here to here. So you access X more or less one pass sequentially. You don't jump back and forth. So this is also good, even for uniprocessor. Okay, so then the question is, what's the distributed representation for sparse matrix? So we have, so let's say one block row has a sparse matrix block row, non-zeros here. And it's actually just a natural generalization of the CRS. So I will have, so this is, I'm using the C syntax here. So I will have this distributed CRS format, okay, the type. And you want to know what is the number of non-zero local. Okay, each processor needs to know number of non-zero local, and each processor needs to know what's your row dimension, and what's the first row, and what's the non-zero value of, so that's a non-zero value array, column index array, row pointer, only local. So we'll take a look at a small example. It's very clear. So that's my small example, 5 by 5. I'm distributing across 2 processors, so P0, P1, okay. And then processor 0 needs to know what is the number of non-zero local to myself. And in this case, it's 5 of them. And what is the M local? M local is the row dimension. So M local is 2. But for processor 1, M local is 3. Okay? So that's not enough. You need to know. And for 0, it's obvious. The first row is 0. But for this processor, you need to know I have these pieces of, this part of the matrix, you need to know what's the first row. So the first row in the global matrix is actually starting from 2, right? So it's 0, 1, 2, okay. And then after that, you do this compressed row representation, 3 arrays. For the first processor, you have SUU is the first row, and then LU is the second row. And the column index for the first one is 0, 2, 4, and then 0, 1. And the row pointer, so the first row point to 0 here, second row start from 3, and then the end pointer. Question about this? So it's the natural generalization, extension of the sequential one. Okay. And then since I think most of you are familiar with MATLAB, how many of you are aware of this sparse matrix thing in MATLAB? Oh, that's good. So quite a few people use this. So sparse matrix has a lot of operations built in for sparse matrix. And it's actually kind of operator overloading, as you can imagine. So when you do create a sparse matrix, when you do operation, if the 2 matrices, all the operands, they happen to be sparse matrix, then the underneath operation is done by sparse matrix algorithms. So for example, if you start with, you do this assignment, use this sparse function, which the sparse function input is a triplet of the non-zeros, the 3 arrays. And then this will generate a sparse matrix representation internally in MATLAB. And in MATLAB, the storage used is a compressed column storage. Okay. And then the operation, you can do multiplication, matrix inversion, like a backslash, solving the system, and factorization, LUQR. For all these operations, suppose your matrix is a sparse matrix, then the output matrix is also sparse. And then if your 2 operands is mixed, so if you have a sparse matrix, and then another matrix, a B matrix, so A times B, for example, if B matrix is full matrix, then they are going to promote the sparse matrix into a full matrix, then do the operation, return your full matrix. So you got to be very careful in your MATLAB code. So somewhere, if you're not careful, you have a mixed operation, mixed operands. the rest of the code is all in dense, in full matrix. So you see maybe it's running very slow. It's because of that. And then there's a lot of ordering, which I'll talk about the next lecture. Minimum degree ordering, reverse Marquis ordering, column AMD, factorization, all this, and then you can use this SPI to see the sparsity pattern. So it's pretty powerful. It's good enough if you're doing small matrix operations, and very easy. Okay, so that's the end of this lecture about sparse matrix basics. So the reference, and I mentioned this templates book, and then there's a sparse BLAS standard. You can take a look. And for sparse, and I mentioned this BBOP effort, the Berkeley optimization group, to do this, to do sparse matrix vector multiplication or triangular solve, try to speed up. And then this paper is very interesting. You can take a look. So that's one, that's more than 20 years ago. They started building sparse matrices in MATLAB. And this paper describes a lot of philosophy that they have, the decision they have made in sparse MATLAB. Okay, so probably not this afternoon, because this afternoon I have to do some MPI exercise. So starting Monday, we'll do some exercise for sparse matrices. Then, so one of the, for example, the first assignment is, suppose you have a program, the matrix is represented as a CRS, compressed row or compressed column, and how do you convert that into another format? Okay, so this kind of, we'll write some of those codes. Okay, so any questions before we move to more factorization type of algorithm? Okay. Just to remind you, all my slides, the updated is at this site. So after each day, after today, what I have talked about today will be, the latest will be there. I won't update that anymore, since I will go forward, not to go backward, to change. Okay, so now we are going into direct method factorization. Could be LU factorization QR, but all these matrices are sparse matrix. And because of the sparse, sparse matrix, we look at the sparse, the graph, and then the non-zero position, etc. They can be random position. Then now you can imagine that there are a lot of manipulation of the sparse matrix we need to do, which has nothing to do with the floating point operation. So that's what we call this combinatorial kind of algorithm. So for this lecture, we'll focus on the combinatorial aspect. So we'll first look at, this factorization. They are used for solving linear systems, right? And then we review sparse Gaussian elimination, and then look at the combinatorial issues. In sparse matrix, there's something called elimination graph, elimination tree, and then symbolic factorization, ordering. You saw a little bit ordering of when you do matrix vector multiplication. And there's more ordering research needs to be done in the factorization and going through the graph traversal, etc. And all these manipulation has nothing to do with the floating point. So it's entirely integer graph kind of operation. So solving linear system, and I'm sure you're all familiar with. And essentially for sparse linear system, there are two big categories. you could solve these iterative methods, for example, conjugate gradient for the symmetric positive definite, or GMRS, the generalized minimum residual algorithm, which is the non-symmetric version, you could say non-symmetric version of conjugate gradient kind of algorithm. And then another class of algorithm is the direct methods, which means that you factor the matrix. So you use Gaussian elimination. So there are pros and cons in each class of algorithm. For example, for the iterative method, people like to prefer to use this for large-scale calculation. It's mainly because the A matrix itself is not changed. And throughout this conjugate gradient, you only need to apply this A times a vector. So that's the reason why I spend quite some time talking about the matrix vector multiplication, because it's such an important kernel. It's a critical kernel in the iterative method. So you can say that suppose you don't worry about preconditioning, then essentially all you need to worry about is A times a vector. So that's what iterative method is nice. It's easier to optimize and parallelize because the kernel is really just SPMV. But it has a relatively low arithmetic, this is a good thing. It has a low arithmetic complexity. And suppose you have numerically you have a good symmetric SPD system. And if you have a good spectrum condition number, then the conjugate gradient could converge very quickly, say in a few iterations. So that it's very fast. For this situation, no other algorithm can beat this. And direct method, we do factorization, and then you will see that it's very complicated for sparse factorization. A is modified, so we factor into L and U. And then it's harder to optimize and parallelize. Numerically, it's more robust. So for matrices, the systems which are very ill-conditioned numerically, then this kind of algorithm without a good preconditioning iterative method usually do not converge. But for LU factorization, it's less sensitive to the condition number. As long as the condition number is reciprocal condition number is bigger than the condition number is smaller than the reciprocal of the machine precision, then you usually could get a very accurate result. But the arithmetic complexity is higher, which we can see throughout the next two lectures. And then these two methods nowadays, it's kind of connected. So it's mainly because the problems, as I mentioned to you, for those big applications, they are yield conditioned, they are huge. So on one hand, you want to use a conjugate gradient kind of algorithm. On the other hand, they are extremely yield conditioned. Without a precondition, usually it cannot work. So very often, people use a direct method factorization kind of technique to build the preconditioner to precondition the iterative methods. So the connection between the boundary between the two classes of algorithms become very blurred right now. People use both. And the preconditioned system, usually it's like this. So instead of solving AX equals to B, right, I'm solving a transformed linear system, M inverse AX equals to M inverse B. And I want this M to approximate A as much as possible, so that M inverse A, the spectrum is, the condition number of this has much reduced, and the spectrum of this is much better. So then the iterative solver, conjugate gradient, or GMRS applied to this will converge very quickly, okay? And very often, this M is obtained by doing some kind of approximate factorization. So for example, incomplete LU factorization, then you apply this M inverse to this. So that's what the whole short course is about, is to build this, either solve this directly using LU or build some approximate factorization to precondition conjugate gradient. So we'll just review Gaussian. I think everyone is familiar with Gaussian elimination. That's, because when I gave this kind of course to computer science students, they don't know anything about this. So I have to start from ground zero. So we do the factorization for step by step, n steps. The first step, we do scaling of the diagonal, and then after that, you have this column vector, row vector, to do the outer product, and then compute this Schur complement, okay? repeat this for n-1 steps. Then in the end, you get the lower triangular matrix, upper triangular matrix. So this part is part of the upper triangular matrix. So then you solve by two triangular solve. And then the big question, this is not a big question for dense matrix calculation, is the stability issue, the pivoting issue. So if you look at one step of Gaussian elimination, so you compute this short complement, and then this is your pivot element. And let's say this alpha is very small. This small guy divided into a normal value. And some of those, this short complement matrix, this update matrix will have a very big element. Then the big element adding together with the original normal element, then this probably some of these normal elements will go away, will not be represented accurately, precisely in the floating point representation. And that's why the algorithm becomes unstable. You actually become inaccurate. You lose a lot of information here. So then the idea here is that instead of doing the direct LU, I do some permutation. For example, for row pivoting scheme, I will every step, instead of using, I look at the current, the entire column, I pick up the largest element and swap to the pivot element, so that I make sure that after this division, my numbers are still in the normal of the same magnitude of this. Then you don't lose any precision there. So then this is something called a controlled element growth. Okay. And the sparse is always complicated. So you can still write the code, in this three nested loop. I can say that I go from the first column to the end, from 1 to n, right? For each column, I do this column scaling operation. So I use the diagonal pivot element to scale into this column. So you are all familiar with this notation, MATLAB notation? So this means we take the jth column of the matrix A. And then after you do the scaling, you update to get the short complement. So this will be two nested loop, right? You go from the I+1 to n here, and then from I+1 to n along the column direction. Then you take each of the element match, each of the pair they match together, subtract into this AJK, which is the jth row and the kth column, so the jth row, kth column. And the only difference between the sparse and dense is since if one of those guys, look at this multiplication, if one of them is non-zero, if one of them is 0, then you don't need to do this operation. So then you save. But of course, if you write code in this way, it's going to be very, very slow. So that's what in sparse case, you cannot, mathematically, that's simple. It's just this. If you just care about math, then it's done. And in sparse case, what's the important thing is something called fill. So what does that mean? It means that's my little matrix, a 7 by 7 matrix. All these black dots, meaning it's the original non-zeros. So I start with the original non-zeros here. But look at this step, elimination. So after this second step, okay, and I have a non-zero here, I have a non-zero here. When you do the short complement update, I get this red dot generated, right? Because of this non-zero and that non-zero, they multiply together, add it together, subtract from this 0. So this becomes non-zero. So this red guy is, we call this fill. It's the new non-zero in the factor. And then the fill is actually propagated. For example, this non-zero, it's the first fill generated due to this non-zero, that non-zero, generated this one. But then continual elimination, and you get another non-zero here, and this non-zero is generated from the new non-zero and the original non-zero. Because of these two guys, you generate another non-zero. So after elimination, you actually generated a lot of this red stuff, the red dots, the fill. And that's something, of course, in dense matrix, everything is filled. You don't have this extra, the new non-zeros. And then so that's a very small matrix. You see already have 1, 2, 3, 4, 5, 6, 7, 8, 8 new non-zeros. But if you blow up the matrix in bigger matrix calculation, and we have seen this field ratio, we usually call this field ratio. It's usually 10 times more. So the field ratio, we define this as the number of non-zero in the factor in the L and U divided by the number of non-zero in the original A. So sometimes it's not even just generated two times more. Very often for two-dimensional problem, you could get 10 times more. And for the three-dimensional problem, you could get 50 times more. So originally non-zero, you have 100. 50 times more, it's 5,000 non-zeros. It's huge. So that's memory. Okay, you have to store those. Okay, so I think I got something. So that's this, because of this non-zero, the field, and in fact, that's what the graph comes into picture. Why do we talk about the graph associated with the sparse matrix? And the useful tool to discover this field is actually this something called look at the graph and look at the reachable set. If you can compute this reachable set, then you can discover all the field elements. So given a certain elimination order from the first vertex to the end vertex, the question here is how do you determine the fillings using the original graph of A? So because you are presented with only the matrix A, you don't know what is LU. And the question is whether you can, based on this A matrix structure, find out what's the LU structure so that you can allocate memory. Otherwise, you don't know how many non-zeros in L and U and where the non-zero position is, then you don't even know how to represent a CRS or a CCS, right? So that's the first question, is identify the non-zero position using the original graph of A. Original graph can be represented by CRS or CCS. So then from the graph, we'll do some definition of the graph. So we define S is a subset of the nodes in a bigger graph. So you have a bigger graph, S is a part of it, a subset of the nodes. And the reachable set is defined, reachable set from Y through this vertex set is defined as all those vertices, there exists this directed path going through all these vertices S and from Y to X. So essentially you have a big graph here. So that's your original graph of the matrix. This is your matrix A, right? And then, so there's a set S. So the reachable set from Y, one vertex here, I want to identify what is the reachable set. So it's just to look at all the, go to X. So go to X1, X2. So you will have a lot of paths which go through this S set, and then all of these reachable, the vertices will be considered the reachable, defined as a reachable set. Okay. And then people have studied using this graph model to find out the non-zero pattern. So it's actually given by this theorem. It says if G of A is the directed graph of A for general unsymmetric matrix, then the edge VW exists in the field graph of A. Field graph is just the LU, the graph of LU, which includes all the filling and all the red dots. Okay. So this non-zero, this edge exists in this LU factor if all of this W is in this reachable set from V through this set, and V1, this set is defined as V1, Vk, and each of these Vi is smaller than minimum of V and W. Okay, so all the internal intermediate vertices here, they are already eliminated. So that's why it means the Vi is smaller than minimum of V and W. So right now we're trying to see whether between V and W, whether there's an edge in LU, whether there's a non-zero field. And then you just look at whether they can be reached through all the already eliminated vertices. That's this theorem. Okay, and it's probably easier for you to visualize this from a matrix point of view. So for example, I start with non-zero like this. And why do we have a non-zero of y here? It's because we have a path. We have a non-zero, I think this picture, so you have a x with a path go to here, 7 has a non-zero, and then it goes to path here, 3. And because of this non-zero, then we generate a path here, 9, and 9 goes to this y. So this path is x to 7, 7 to 3, 3 to 9, 9 to y. Does that make sense? Yes. So from matrix, if you look at the factorization process, elimination process, this non-zero and that non-zero, it will generate a non-zero here. And then this non-zero and that non-zero will generate a non-zero here. So that's what this reachable set is about. So then from computer science, the graph point of view, in order to find the field, it's equivalent to find the transitive closure of the original graph of A. So this is something called a transitive closure. Basically, you look at all the reachable sets and make them connect becomes one edge. And then that's get all the field. Oh, sorry. So that's what's happening here. I was trying to, okay. So from matrix point of view is you have a non-zero here. That's the original non-zero, then which generate a field here, okay? And then this field coupled with this non-zero generate another field. And that field coupled with this non-zero generate another field here. So that's the whole path in a directed graph. Okay, so I think we have, let me see where, we have 15 minutes. We can do the, yeah. So we can go through a little bit sparse elimination process with this graph model. And this is a simple, the graph, the picture shows the sparse Cholesky factorization. So Cholesky factorization, it just means A is a symmetric positive definite matrix. So you can factor this as L, and the upper triangular matrix is the same as the lower triangular, but it's transposed. So they pairwise, they have the same value. The pseudocode for this will be from first column to nth column. And the first column L, we just assign this. For each of k smaller than j, so look at this jth column, and I want to see which of the column will update into here, right? So it depending on the non-zeros here. For example, here, if for each of the k smaller than, this is the jth row, jth column, for each k smaller than j, so look at all the entries here, for each non-zero, and it's going to have a match, it's going to have a matched column here, then it will update. You will have, this is like a sparse C mode, is C modification, it's a column modification. So you will need to use this LJK, one of these non-zero, multiply the whole column and add it into your current destination column. Okay. Is any question about this operation? Maybe it's easier to draw a picture. Okay, so this is your jth column. Suppose this column has only 2 non-zeros, right? So then the update to this column will only have, all these columns will be updated into here. And then similarly, all this column will be updated here, okay? So all the 0 columns, you don't need to update there. So that's what this, if LJK is non-zero, if one of those LJK is non-zero, then the whole column, the kth column, will be updated into your current column. And then after that, this is after this update operation, then you will have to do this square root, take the square root of the diagonal, and then scale this diagonal by the scale this current column by this diagonal. And then the field path theorem tells us that after x1 to xi are eliminated, the set of nodes adjacent to y in the elimination graph will be given by all these reachable from x1 to xi, given from y to there. So you can identify from this path what are the non-zeros in this column. Okay? Yes?
So the theorem doesn't take into account like the weighting of the nodes. So is it possible that you may identify something as non-zero, but because of the weights, it actually is a zero?
Because of the weight? What do you mean the weight?
Well, maybe I don't understand the theorem. So, I mean, you're using a theorem so you can allocate memory for the non-zeros.
That's right. Yeah. So you use this theorem. You know that how many of those it will end up in this column. How many non-zeros will end up in this column, right? So look at this picture. Suppose this column has only 2 non-zeros, right? 2 non-zeros here. And then that column has 1 non-zero. So then these 3 non-zeros will be, and there are 2 non-zeros here. So these 3 non-zeros will be propagated into here because of this, update, the non-zero update, Gaussian elimination, right? So this non-zero propagate these 2 non-zero into this position. And that non-zero causes this another zero here, another non-zero into here. But before you're doing this, this position in the beginning could be 0. And it could be non-zero. It's only after elimination. After elimination of those variables, it becomes non-zero, right? Yes?
So there is no pivoting going on here at all.
For Cholesky, there's no. We just follow the diagonal.
Can't you still pivot?
What do you mean pivot? For numerical purpose or for?
Yes, compute the matrix.
Yeah. So.
Interpretation from left and right.
Right. I'll talk about that later. So right now, I'm just assuming that we just go through this order. So we can do pivot ordering, etc. We'll talk about that later. But this is just the underneath how this works. If you suppose I follow this order, then step by step, each column I'll generate this non-zero like this. So then so this is the graph, for example, of the small matrix. After you find the Cholesky factor, I get these non-zeros like this. And for this small example, I have only 4 new non-zeros, 4 fillings, right? And then you look at the graph of this Cholesky factor. Before, I'm not sure whether this graph matches this. So before, I don't have 8, 3, right? So where's 1, 2, 3, 4, 5, 8? 1, 2, 3. So actually, this graph probably is not quite the graph of this. So this is the graph of LU with red edges corresponding to the new non-zeros. And then you can reduce this graph, have a compressed graph, something called the elimination tree. It just to say the first column will update third column. The third column will update 7th column. But the 6th column and the first column, they don't have any, they are independent from each other. They don't update each other. Okay. Then this tree, each node of the tree corresponding to 1 column of the matrix, and each edge corresponding to the dependency, saying which node will update which parent node. And with this elimination tree, you can use this parent definition. For each node j, you can say what's the parent of j. So parent of 1 is 3, parent of 8 is 9. This single one-dimensional array of size n gives you this parent, the elimination tree representation. And that can be used to help you to design your algorithm and then to even design the parallel algorithm in the future. So this tree describes the dependencies among the columns of the factors and also can compute the field factor, the graph of L and U very easily from this tree, and also can compute this tree very quickly. We can actually, based on everything, we can based on the original matrix graph of A, then to compute this tree in linear time. So that's a very fast algorithm. So then the big thing in sparse factorization is something called a symbolic factorization. And I will not spend any time at all to talk about this operation. It's very important in any sparse matrix factorization software. They will have to do this. So what does this do is before you do this numerical factorization, there's a pre-processing step. Before the numerical factorization, you compute the elimination tree to identify the dependency. For example, here, this column is dependent only on, if let's say this index is 2, this index is 6. So that means this column is dependent only on column 2, and that one is 6. So then this column doesn't depend on column 1 because column 1 here is 0, right? So that's the dependencies. And then this part of the tree for this picture will be J. This node will have 2 and 6. Maybe something like that. Not quite. So part of the tree will be like that, dependency. So after you compute the elimination tree, then you can, based on the tree, you can count the number of non-zeros of each factor. Then you define supernode. I will talk about what does that mean. And later you have non-zero structure of L and U. This you can all compute it as a single symbolic factorization. And depending on whether you are doing the different operation, it's a Cholesky factorization or LU factorization, this operation, symbolic factorization, could be complicated. In the symmetric case, Cholesky factorization I just mentioned, then this operation can be very fast. You use the elimination graph of L, and it's a transitive reduction, which is elimination tree. Then the complexity could be linear in time in terms of output. So it's linear in the number of non-zeros of L factor for the Cholesky factorization. So this symbolic factor is very fast. But for the LU factorization, it's more involved because you have two part L and U. They are different. So the two graphs, they are actually, you need to deal with the two graphs. So the transitive reduction here is actually something called the elimination DAX. It's a directed acyclic graph. And then there's some technique to improve the speed of this. And also you can improve by grouping the super variable together. So then the complexity here is greater than the number of non-zero of this, but it's still much smaller than the floating point operations needed to compute this LU factor. So this symbolic factorization basically is a pre-processing step. It's relatively much faster than later you are doing the factorization, but it's very much involved using all its non-floating point operation. It's all integer operation, graph operation. Okay. So I think the question someone asked about permutation, that's coming. I think we can, what time is it? Maybe we should just mention what's the issue here, and we'll stop. So the question is, naturally, it's inevitable to get the filling, get this red stuff. Then the question people naturally ask is there any better way to permute the matrix or reorder the equations and variables so that we get as few filling as possible? So the classical example in the textbook you can find is suppose your matrix, this is one example, your matrix, we call this arrowhead matrix, right? So you have the first column is non-zero, first row non-zero, diagonal here, and everywhere else is 0. And what happens if you do this elimination order? What's the LU factor? They're full, yeah. So after the first step, you do this outer product to update, everything will be filled, right? So with this order, and you will get the full matrix. And then right now, I'm saying is I reverse the order. I permute so that the last equation first. So do a reverse permutation on both sides. So I permute multiply by this permutation matrix on the left and the same permutation matrix on the right. And then I change the order. It becomes this order, okay? with this order, what's the outcome when you do Gaussian elimination? Is that simple?
Yeah.
Yeah. What it is? What's the structure? Yeah, we don't worry about the value, just to say the pattern. Yeah, non-zero pattern.
All non-zero, or all zeros.
All zeros? It's the same. So the values might be different. Well, you have to do calculation, but then these zero blocks, they preserved. So in the end, the LU factor, you still have the same structure as the original. So no field at all. Okay, so this is a very extreme situation. And usually it's somewhere in between. So we have to find a good ordering. We call this to reduce the field, right? So somehow to start with a matrix like this, you try to find a permutation so that you get a better structure like that, and then do Gaussian elimination then without field or with reduce the field. That's the whole purpose of ordering, so which we can catch up from next time. Continue, okay?